Colligative properties are properties that depend on the number of particles, not the type of particles. In this example, the blue are the solvent particles, while the yellow and red are two different kinds of solute particles. Even though Group 1 has yellow particles as the solute and Group 2 has red particles as the solute, they would exhibit the same colligative properties because they are the same relative number of yellow and red particles.
Freezing point depression, boiling point elevation, osmotic pressure, and vapor pressure lowering.
Freezing point depression, boiling point elevation, and osmotic pressure generally only involve one step and are fairly easy to calculate. Vapor pressure lowering, however, can be more complicated and sometimes involves two or more steps. We will be focusing on vapor pressure lowering today.
The vapor pressure of a liquid is the pressure of the gas above a liquid when the two are in dynamic equilibrium, or when the rate of condensation and the rate of evaporation are equal. In this case, the vapor pressure would be the pressure of the floating M&Ms up here.
Vapor pressure lowering occurs when a solute is added to a solution and the solute particles begin to interfere with the ability of the solvent particles to vaporize. This leads to an overall decrease in the rate of vaporization. If we add blue solute particles to the solution, the orange solvent particles aren't able to vaporize as well, thus lowering the overall vapor pressure.
Raoult's law is an equation that quantifies the vapor pressure of a solution. In Raoult's law, the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent at the same temperature. There are two different substances present in the solution. What is the vapor pressure of a solution when 58.9 grams of hexane is mixed with 44 grams of benzene at 60 degrees Celsius? The vapor pressure of pure hexane at 60 degrees Celsius is 573 torr, and the vapor pressure of pure benzene at 60 degrees Celsius is 391 torr.
Assuming the solution is ideal, we can use a variation of Raoult's law. Raoult's law says that the pressure is equal to the mole fraction times the pressure of the pure solvent. In this case, since there are two solvents, we have to set up a PA for hexane and a PB for benzene. The total vapor pressure will be equal to the partial pressure of hexane plus the partial pressure of benzene. To find the pressure of hexane, we have to use the mole fraction of hexane times the pressure of pure hexane, which is given in the problem as 573 torr. To find the moles of hexane, we use 58.9 grams of hexane as given in the problem over 86 grams, which is the molar mass of hexane. We get 0.685 moles of hexane. To do benzene, we use the same process and use 44 grams of benzene over 78 grams to get 0.564 moles. To get the mole fraction, we use the moles of hexane, which is 0.685, over the moles of hexane, 0.685, plus the moles of benzene, 0.564, to get 0.548. We then plug in the mole fraction of hexane to find the pressure of hexane, 0.548 times 573 torr as given in the problem to get 314 torr. Using the same process on benzene, we get that the mole fraction is equal to the moles of benzene, 0.564, over the moles of benzene, 0.564, plus the moles of hexane, 0.685, and get 0.452. Plugging in the numbers and 391 torr for the pressure of pure benzene, we get 177 torr. Adding them up, 314 torr the pressure of hexane and 177 torr the pressure of benzene, we get 491 torr.